Okay, so I said I would do a video lecture quick on how to use Dalton's law of partial pressure to solve a problem. So here is a problem that where a gas is collected over water. It's collected at 50 degrees Celsius, and it gives us the atmospheric pressure is 96 kilopascals, and it wants to know what is the partial pressure of oxygen. And then ultimately, we're going to figure out how many grams of oxygen gas can be collected if you collect the gas over water. So if you collect a gas over water, it assumes you know that the gas is not pure. It won't tell you that, but that it's a mixture. Okay, and so the total pressure in that tube that you'd be collecting the gas, and this one would have oxygen gas and it would have water. How much water, though, is solely dependent on the temperature of the water. And it says it's collected over water at 50 degrees Celsius. So that's a pretty warm temperature. We have to get that value from a water vapor chart. Okay, so if we look at it, at 50 degrees Celsius, water, liquid water, enough water molecules will, like, basically this value is telling you how many water molecules are going to evaporate at that temperature, because that's going to create the pressure exerted by those now gaseous water molecules. And it's 12.3 kilopascals. So we've got 12.3 kilopascals, and atmospheric pressure. Okay, if this gas is collected over water, that water has to be exposed to the atmosphere. And so total pressure is going to be equivalent, P total is equivalent to atmospheric pressure. So here we can put the 96.00 kilopascals, and we subtract the 12.3 kilopascals here, we will get the partial pressure of oxygen. Now with sig figs there, your calculator will display 83.7 kilopascals, which is also right with significant figures, because this is a measured value. That chart is telling you it's 12.3, and so it's limiting our amount. If we had a water vapor chart that gave us more precise values, then we could use it. But this goes to 2 pass, that goes to 1 pass, so 83.7. So in that 80-liter tank that we're collecting the oxygen gas, only of the total pressure in that tank, only 83.7 kilopascals is exerted from the oxygen gas. The remaining pressure that would be red in that tank would be created from the water vapor. So in that tank then, it's not a pure gas, if we want to know how many grams of oxygen gas are collected after we have done that first part, okay, so if we want grams, we need the amount. We're not at STP here, and so we now have the pressure of oxygen. So we can't use the total pressure unless we know, if we were to convert the amount of, like, this amount of pressure would equal how many water molecules, then we could use the total pressure value, but we don't have that, okay? Now the volume is the whole volume of the tank, and we're gonna need to know how many moles of O2 to then get to grams. So to get to moles of O2 here, we're gonna set it up like so. So the pressure of the oxygen is 83.7, and that's its contribution. So that's going to determine then how many oxygen molecules there are. It's in an 80-liter tank. Let's use the R value that uses kilopascals, 8.314 kilopascal liters moles per Kelvin. And the temperature, what was it? It was 50, was it 50.0? 50.0, so 323.0 Kelvin there. And so the moles I get here of oxygen with sig fig. So we're going to get just 3. So moles of oxygen gas in that tank is 2.49 moles of O2. And then if we want how many grams, like if we were to weigh it in 1 mole of oxygen, it would be 32.00 grams of oxygen gas. I'm going to take that. I'm going to take my unrounded answer in my calculator, multiply by 32, and not take the 2.49, and I get 79.8 grams of oxygen gas there in that tank of 80 liters. So it's usually just like a precursor to using the ideal gas law that you have to sometimes take into consideration, because if I had used the total pressure there, I would have gotten more oxygen than actually was there, because the oxygen gas did not make up it was not a dry gas. So it did not make up this total pressure that would be inside of that tank that was collected. So hopefully this helps frame out Dalton's law of partial pressures a little bit within the context of an ideal gas law problem and just seeing its application.